Alrighty. Welcome back to part two of our week 7 CAD session. In last session, we created this layout sketch here that represents our pneumatic joint that we're making. In this session, we're going to actually go through and we're going to model the parts. And then next week, we're going to put together the assembly and import the components and set up all that stuff. So really quickly here, I'm going to rename this to just actually, oops, there we go. And rename that just to make it a little more clear. As we get kind of later here in the CAD class, I'm going to start trying to kind of name some things and maybe do some part numbering and everything just to kind of keep things neat. Okay, what we're actually going to do here, we're actually going to use this sketch to kind of model some of our components. We're going to model all the components in this one part studio, and then we're going to do things a little bit more advanced on the assembly side, but we'll get into that next week. So I'm going to rename this sketch as layout just to keep it clear. So what we're going to do first is we're going to extrude this rectangle because we already drew this tube, so we can just extrude it. I'm going to do symmetric, and it's going to be 1 inch because it's a 1x1 tube. We're just going to extrude this as a block, and then I need to turn visibility of the sketch back on. Oops. And then we're going to extrude, actually, we're going to go ahead and just run the tube converter now on this guy. And thickness of 1/16 of an inch is fine. And we actually want this whole pattern, so we're going to let the tube converter make the whole pattern. The nice thing is, because we kept this tube to a nice fractional length, like in increments of 1/2 inch, we can just create a whole pattern and it's fine, right? We could buy pre-perforated tube, like tube that already has the holes in it off the shelf, or we could, set up some stock in a tube jig and just have it run have the router run a bunch of holes for us before we cut the tubes to length. So having a nice pattern like this is nice. Okay, so the hole spacing is 1/2 inch. That's what we want. The hole size is 196. That's fine. That's clearance for number 10. Looks like these defaults here are still good. So if your tool does not look like this on your screen, just pause the video and look at what we're doing here. We're going to go ahead and allow it to put holes on all 4 sides, even though I think we're only going to use the holes on this side and the one opposite. The top and bottom are not really relevant for this project. But we're going to go ahead and put all the holes in just because. Okay, so that tube is there. Now let's create nope. Let's just extrude this guy. Symmetric, 1 inch is fine. Create a new part and then run the tube converter again, and the same hole settings should work as well. Now, like I said before, if we look at the layout sketch, this line here does not line up nicely with this hole. In reality, what we're going to do is we're going to model a bracket that picks up these holes and then also just has kind of a weird offset on it that picks up this point out here for the pivot of the air cylinder or for the clevis. That's a pretty good way of doing things. Right? Keep all your hole spacing on your structure to be nice, even increments. Keep all your structural elements to be nice fractional lengths, like 1/2 inch increments preferably. And then if you've got any weird geometry, kind of bundle all of that weird geometry into the brackets that attach to the structure, right? It's pretty easy to cut some weird geometry, especially using a CNC router. Right? You can cut some like very funky shaped brackets and create very weird geometry with the CNC tool. Whereas if you're just buying tubing off the shelf that has a hole grid in it, then you don't have a lot of control over where exactly those holes are. So it's nice to just assume your holes are on a nice fractional spacing in your structure, and then any weirdness you bundle into your brackets. So we're going to just go ahead and click OK here. And then I actually don't like looking at the default colors, so I'm going to edit the appearance, edit the material, set this to 6061, and then edit the appearance, and I'm going to set it to this light gray. Okay, so then now what we need to do is we need to start modeling our brackets here. So basically, we can start kind of anywhere, but I think let's start up here with this main pivot up at the front. So what we're going to do here is we're actually going to put some bushings in this tube, and then we're going to have some brackets that are spaced out from this tube here that then go up, and then there's going to be basically a standoff that goes through and gets bolted from either side, and that's basically going to be the the pivot for this mechanism here. Wouldn't necessarily always do the pivot that way, but that's how we're going to do it for this example. And then over here, we're going to do something kind of similar. We're going to have, a bracket that bolts on and kind of comes up here, supports the cylinder. This one's got some extra considerations we'll get into a little later. And then there's going to be just basically a pin or a bolt or something that goes across to support the air cylinder itself. Okay, so let's talk about this bushing, because this is actually going to become a relatively large factor here. So first thing we need to do is decide what diameter we want for the pivot shaft going through here. It could be a 1/4 inch, or it could be something a little larger. I probably wouldn't go smaller than a 1/4 inch. So we could do 1/4 inch. We could do 3/8 would be a nice size. So let's actually go here. Actually don't need these. Both of these open. We're going to go back to McMaster-Carr, and then we're going to look at bushings. Oops, I should do bronze bushings. Now I will say we haven't really touched on this much in the CAD class up to now, but most FRC teams order a lot of stuff from McMaster-Carr. They have very fast shipping. They have a very wide range of products. Their prices are a little bit more on the expensive side. However, the convenience of their website and everything really just saves a lot of time in the build season. So the extra cost that they have for some items is worth it. The other big thing, and this is probably maybe the number one reason to use McMaster-Carr, is that they have CAD for most of their products. So when you're designing a robot, having CAD is extremely important, because if you're trying to buy a product and you don't have CAD for it, there's no way for you to evaluate how that product works in the robot design. So that's another big advantage that McMaster has. So I have no problems teaching the CAD class, teaching this CAD session, and essentially just teaching you guys how to use McMaster-Carr's website, because there is a 100% chance that if you're designing a robot, especially on RoboChargers, you will be using McMaster-Carr's website as you do it. So it is pretty frequently, pretty much, I'm pretty sure everyone in FRC who's designing a robot has McMaster-Carr open, on their computer when they're doing CAD. It's just kind of the reality of how these robots are designed most of the time. So we're going to kind of go here. I want a flanged sleeve bearing because we need something to hold it into the tube and keep it from falling out. So we're going to go down here to these oil and bladed flange sleeve bearings. There's all kinds of options for bushings, but just to kind of keep this project simple, we're just going to use these. We're going to do inch. We're going to look at 1/4 inch, and I think we'll look at 3/8 inch shaft diameters as well. Kind of just look at what our options are. So what I'm going to look for is this 4 housing ID, because basically this is the 4 housing internal diameter, right? And basically this is just what internal diameter, what hole do you need for this bushing to go into, right, is what that means. And so for a 1/4 inch bushing, we need a 3/8 hole, or if we go up, there's several different sizes here. There's some 3/8 ones, there's a 1/7/16 size, which is a 1/2 inch long, which is not actually too bad, that's okay. And then there's some 1/2 inch sizes. So all those are pretty reasonable. And then we go down here to the 3/8 shaft diameter ones. We've got some 1/2 inch ones, we've got some 9/16 ones, we've got some 5/8 ones. So let's go back to our CAD real quick, and let's go to the hole feature. We need to create a hole here for these bushings. There's going to be one bushing in this side with a flange, and then one bushing in this side with a flange. So we're just going to drill a hole all the way through. So we're just going to custom, and we're going to just go like 1/2 inch to start, and then we're going to just pick this sketch point, and then the merge scope is going to be this tube. Oh, it's only doing, that's not going to work. Okay, let's just do this. This will be easier. I'm going to create a sketch on this plane, and then I'm going to just click, I'm just going to select this point and hit project. And then I'm going to create the whole feature using that sketch. And then the merge scope will be this tube. And this will be custom 0.5. And it was just giving me an error there because it was drilling a hole that was already there and it wasn't actually doing anything. Okay, so this is what a 1/2 inch hole looks like. The other sizes were 3/8 is really small. I'd prefer to do the 3/8 shaft just because it's a little larger. Could also do a 5/16 shaft, but that's like a little bit of a weird size. So I'm trying to avoid that. So we can get 1/2 inch bushings. We can get 9/16, we can get 5/8. So 9/16 is 0.5625. I just have these fractions memorized. That's not too bad. If we go up to 5/8, which is 0.625, this starts to get a little thin. This starts to make me a little nervous that we're compromising the strength of the end of the tube. It might be okay. It really just depends on what this mechanism is, like I said. That being said, because we have access to the 1/2 inch ones, I feel like that might be the way to go. They're also going to be cheaper too. So let's do that. Let's just plan on doing the 1/2 inch ones. The only difference is it just makes the wall thinner, and so for higher loads, they're not as good. So because we've got a bushing on both sides, we have to make sure the bushing's not so long that the two bushings hit each other in the middle. It's okay if they touch, it's just there can't be a gap. So the length here can't be more than 1/2 inch. I'm actually going to go, let's look at this one. It's a 1/2 inch long, which means the bush, I don't remember if the length is, I don't know, length is from the outside of the flange. So I think this is the bushing we'll use. This is a pretty reasonable size. We probably have some of these in the shop. This is a relatively standard size, a 1/2 inch length. So we'll plan on using this bushing here. So now in reality, what we're gonna do is we could download the CAD model and import it into Onshape and constrain it in the assembly. But in reality, like this is such a simple shape, it would literally be faster to just model it. So that's actually what we're gonna do. So what we're gonna do here is we are going to model. I'm actually gonna. There's a number of different ways you could do this. You could revolve it. You could extrude it. You can do whatever, right? What I'm gonna do here is I'm gonna create a sketch on this plane, and I'm gonna model just the flange because I think that's easier. So what I'm going to do here is I'm going to draw 0.375 ID and 0.625, I think it was, question mark. Flange OD, yeah, 0.625, and then the flange is a 1/16 of an inch thick. So I'm going to extrude this out. I'm going to switch to new because I want to create a new part, 625. And then I'm going to create a sketch here. This is a little bit unintuitive, but you'll see why I'm doing this here in a second. I'm going to select the inner diameter and use it, and then I'm going to make this a 1/2 inch. And then what I'm going to do is I'm going to extrude this, except I'm going to flip the direction, and I'm going to merge it with this guy, and then I'm going to set the length to 1/2 inch. And this is why I created the sketch on the front face, even though I'm extruding back into the part, because I can just make the extrusion length whatever the length of the bushing is, and don't have to figure out what the length of this, like the barrel part, is by itself. So that's just kind of a convenience thing there. Okay, and then we have a bushing. And then what I typically do is I go over here. Whenever I do this, I go here, I select the part number, I hit Control C to copy it, go over here, click rename, and I paste. I just put the part number in here. And I know this part numbering scheme here is unique enough that just I can tell just by looking at it that it's a McMaster part number. And so when I look at the list of parts in this assembly later on, I know that I need to order that part from McMaster is basically why I would do this. And then the other thing I'm going to do here is assign material. I'll just kind of just bronze, whatever works, doesn't matter. Just as long as the density is close, that it gets a weight calculation reasonably close. And edit the appearance. I usually do like this one here for bronze because it's kind of a brown brass type color. Okay, and then I'm not going to model the one over here. We'll do that in the assembly. That's okay. Okay, so then what we're going to do here is, now that we've got this part in place, what we can do is we can kind of continue modeling some of the other parts here. So what we're going to do is, Yeah, okay. So what we're going to do is we're going to model kind of this bracket next. Now what's going to happen is, if we look at this from the end, um, we're going to have a bracket that goes here on the outside of this bushing. Now the problem is that this bracket can't just attach to this tube because um, because of the flanges sticking out, and so these two tubes are, you know, not flush to each other basically anymore because the flanges here are kind of interfering. So what we actually have to do is we actually do some layering here, and there's a variety of different ways to solve this problem, but the easiest way to do it with the RoboChargers manufacturing techniques is we just cut a plate that acts as a spacer, and then we cut the big plate that goes up here and actually supports this pivot, and we just layer them on top of each other, and we just rivet them together. So now, one of the things to understand is that if this plate, the thickness of this flange and the thickness of this plate matter, right? Because if this plate happens to be slightly smaller than the thickness of this flange, then what'll happen is this joint will be really tight, and the main plate that comes up here will rub really tightly against this flange. Now, the part of the purpose of this flange is to kind of act as a thrust bearing. That's something that flanged bronze bushings are really good for. However, if we tighten it down too tight, you know, this shaft that's going through, if it pulls everything in too tight, this thing won't be able to pivot easily. So it's important to actually build in a little bit of a gap here, a gap between the main plate that extends up here and the bushing. So that can actually be a little bit challenging though, because you know this piece of material that's down here acting as a spacer is not actually, you don't actually have that tight of control over the thickness of that part. So there's a few different solutions. So first of all, you can just find a material thickness that works, right? A material thickness that's actually slightly thicker than the flange. And it's important to understand that a lot of materials, even though, you know, the material thickness is listed as being some, you know, fractional number or some number, the actual, what you actually get out of that material is, you know, not quite that number, right? That's especially true when you're working with like polycarbonate. You know, you buy 1/8 inch polycarbonate. It's not actually 0.125 inches. It's typically closer to 0.11 inches. So it's actually a little thinner. And so if you're relying on that material to be a spacer for something, but it's actually thinner than you think it is, you get yourself into trouble. So typically what you would do here is you would use like a 1/16 inch piece of aluminum because this flange is a 1/16 of an inch thick. But, you know, if that 1/16 inch piece of aluminum is slightly undersized, which if I remember correctly is typically the case, then this joint ends up being too tight. Now, in an FRC context, that's not necessarily that much of an issue, because what you can always do is take this bushing over to a sander, sand a little bit off of it, and then all of a sudden it's not tight anymore. And so really I'm kind of blowing this out of proportion. I'm making this sound like more of an issue than it actually is. On FRC robots, because you're only building, you know, at most 3 robots in a season, if you're like you know, a crazy top end team where you're doing a lot, right? Most teams are only going to build 2 robots, you know, if they want to practice in a competition bot, and the vast majority of teams are not even going to do that. They're going to build 1. And so it is actually okay to rely on some kind of, I guess, a little bit more manual fit and finish processes on your robot, and not waste a bunch of time fiddling around in CAD trying to make it work perfectly in the digital world when you can spend, you know, 2 minutes on a sander fixing the problem in the real world. As long as you're aware of what some of these problems are to the point where it doesn't cause delays during the season, as long as you understand that like this bushing needs to be sanded down and you let someone know that that is the intention, it's important to document these things. However, it is totally okay to rely on that to make the mechanism function. You know, another thing that might, for stuff like this, like if this bushing were to fail at a competition, you have a spare, it wouldn't be so easy to sand this bushing down at a competition. So it would be important to like make sure that you plan for spares for some of this type of stuff, you know, pre-sand down a bushing or something, or before you leave for a competition, steal one off your practice spot or whatever, right? There's some things you can do. So now, all of that being said, there's actually kind of a nice coincidence. The RoboChargers actually are, you know, actually kind of have a nice solution to this problem, because we were actually donated a bunch of 0.080 thickness aluminum a number of years ago, and we actually use that for all of our structure just because we've got sheets and sheets and sheets of it. Um, we're going to continue using it until we run out, basically, and then we'll probably buy some 16th inch or something. I don't know. And so we actually design a lot of stuff with this 80 thou thick sheet. And so actually using 80 thou thick sheet here is actually perfect because this flange is a 16th of an inch thick. And so we end up with that 80 thou gives us 20 thou of clearance on the outside of this bushing here. Which is pretty much perfect. It might be a little looser than we'd want, but honestly, I would say that's perfect, especially for something like an intake where this being able to wiggle back and forth is not an issue at all. So I'm gonna basically stop talking now, and we're gonna just model this plate, and we're gonna make it 80 thou thick, and that just solves our problem, right? We don't have to worry about the spacing at all. We don't have to sand any bushings. We don't have to worry about anything. So I'm gonna create a sketch on this surface here, and what I'm gonna do is I'm just going to create a rectangle. It's pretty easy. And I'm just going to need to decide how many holes here I want to pick up. I want to pick up quite a few because, if this were the pivot for an intake or something, I don't want to have just only a couple of rivets or a couple of bolts holding this in. So this would be, for the RoboChargers, this would almost always be rivets. You need 3 minimum. If you're doing a riveted connection, absolutely no less than 3 rivets, for especially something structural. If it's some little bracket for a sensor or something, maybe you could do 2, but for structural stuff, it's got to be 3 at least. I'm going to do 5, and I'm actually going to put the end of this part in between these holes in case I wanted to use this hole for something. So what I'm going to do is I'm going to dimension from here to those. Oops, I need to actually use this hole, turn it to construction so it doesn't get in my way later. Dimension from here to here, 0.24. And I'm just going to let the part go all the way to the end of the tube out here. I could shorten it a little bit, and that would save a little bit of weight, but honestly, it's not worth it. And then in addition to that, it'll be flat. The part that comes up here and captures this I'm going to want that to go all the way to the end of the tube. So having that extra support there is nice. Okay, so then what I'm going to do, actually, now that I think about it, I'm actually going to not switch this to construction, and I'm actually just going to select all these holes and put them in the sketch. Now, normally, I would like to do this with the whole feature, but the fact that they're already there and I want them based off of the tube's geometry, projecting the holes through like this, I think is okay in this situation. So I'm going to extrude this out. I'm going to do new instead of add. It's trying to just add onto the tube, which I don't want. This is going to be 0.08. If you're not on the RoboChargers and you're designing, with your own materials in mind, keep in mind that 0.08 material is not a very common size, and so for the RoboChargers, that's a thing we work with pretty frequently, but every team is not going to have access to that. Okay, so then what we're going to do is we're going to create another sketch on this surface, and now we're going to create the actual bracket that holds the pivot. Now what I'm going to do here is I'm going to use lines. I'm going to go up to here. I'm just going to hit escape, and then I'm going to actually just project these 2 edges here. Because I just want it to match whatever this bracket is. So if I go down here and I change this bracket, I want the bracket on top to update. So projecting geometry like that is useful. And then I'm going to go back to this surface here, and I'm going to grab an arc. I want to make sure, I got the center point arc here. And I'm going to just kind of throw this down here. And then I'm going to constrain the center point of the arc to the pivot in the sketch. Now, when I'm doing this, I try to constrain as much stuff to the sketch as I can. I don't want to constrain things to I don't want to constrain things to this bushing, right? Because if I come back and I change something about this bushing, I don't want to break all of my sketch constraints. And so constraining things to the layout sketch is kind of your best friend in that case. I'm gonna attach, I'm gonna go here, attach these 2 as well. And I'm actually gonna go, and select this line and this arc, and I'm gonna make them tangent to each other. And then I'm gonna go from here, select that, and connect down there. And then I'm going to make these tangent as well, and that should be it. Okay, everything's constrained. And then what I'm going to do again is I'm going to grab the holes from the bracket, project those through, and then what I'm also going to do is I think I'm going to just go ahead and put this hole in here. Yeah, that's okay. This is another situation where it'd be nice to have, this is such an important hole that I'm okay putting it in the sketch. If it's just a mounting, if it was just some mounting holes, I'd rather do it with a hole feature. But this is such an important hole that I kind of want it in the main sketch just so that all the geometry is defined in one place. This is just going to be at number 10 screw, and then we will do a standoff through here, which we'll model here in a second. Okay, and then this is also going to be 0.080. If this was like a super high load joint, we might do a thicker material here, but for the purposes of this exercise, we're going to do this. RoboChargers typically use, oops, I made a mistake. This should be new, not add. Okay, two separate parts. RoboChargers typically use the 80 thou, then we use some 1/8 inch aluminum and some 1/4 inch aluminum. Every once in a while, some 3/16 as well. And then we use typically 40 thou polycarb, 16th polycarb, 1/8 inch polycarb, 3/16 polycarb, and 1/4 inch polycarb. And then last year we actually used 3/8 polycarb as well for a couple of things, but we don't use that often. Okay, so then if I go to the back view here, you'll see there's this nice little air gap between the parts. The spacing is perfect, and everything's happy there. Okay, so then what's going to happen here is we need to create a standoff that goes from here and it basically is just symmetrical on both sides. Now, what we could do is we could calculate out what the length is, right? Like from here to, you know, the right plane, which is the mid plane of this whole thing, is 0.58. We could multiply that by 2 and make the standoff, you know, go in here, create an extrusion, extrude it out, double that length. However, that does not, if I were to change the width of these tubing or change the width of the spacer or whatever, the standoff wouldn't update, right? So what I'm actually going to do is I'm going to create it in kind of a weird way, and then I'll kind of explain, you know, why I did it that way. So what we're going to do first is we're going to create a sketch on this. Actually, no, I'm going to create a sketch on the right plane, and what I'm going to do is if it will let me go to the right view here. So what I'm going to do is I'm going to do just a 3/8 inch circle attached to, once again, I'm attaching it to the sketch point that's still here. Then I'm going to extrude this, and I'm going to do new is fine. I'm going to up to face. I'm going to do the inside face of this. And so this is basically like half of our standoff, right? I'm still new. Click OK. And then what I'm going to do here is I'm actually going to go ahead and add a tapped hole in the end while we're here. So create a sketch, project. Actually, I'm okay not attaching this to the sketch because I'm just going to project. Wait, what? Why not? That's strange. Okay, all right, I guess I am projecting this point. Come on. There it goes. All right, so then click OK on the sketch. I don't know why this is showing up blue. There's some weird thing going on here. I don't really want to troubleshoot it right now, though. Okay, so simple is fine. Through, we want blind. We want NSI, tapped, number 10, 32. The default depths are okay. Sketch points, select that. Oh, I guess the depth is basically full depth anyways, or it's going to end up drilled all the way through. That's fine. Okay. Click OK. And then what we're going to do here is we are going to do, wow, this like sketch is really messed up. Something weird is going on here. Hang on, I'm trying to troubleshoot what's going on here. And it's very strange. All right, I'm just going to refresh this page. I think it could just be a graphical glitch, actually. Yeah, it appears it was. Okay, all right, cool. Just a graphical glitch, no actual functional issue. Okay, now what we're going to do, we've got the part that's got, you know, the, it goes up to the mid plane, and then it's got this hole in the end, and then we're basically just going to mirror this part. So I'm going to keep this on a part mirror. I'm not actually going to do a feature mirror. Select the part, select the plane, which is going to be the right plane. I could also pick the end of the part, but I prefer to base things off the origin if I can. You'll see we get this ghost here showing us. And then we want to do, the merge scope should be the part itself. So it'll mirror the part, but it'll combine it into one part at the same time. So we click OK. Cut out there. But anyways, if we mirror the part and we select part 6, we can see that we've got the standoff that goes all the way through. Okay, moving on here. Let's just make sure that we have everything in place here. Let's go ahead and set some materials. So part 4 and 5 here. Let's assign the material. These would be 50-52 aluminum because they're sheet stock. This part in here could be, just about anything, but I think we'll just assume it's 60-61. This would be like, we would just take a piece of like 3/8 aluminum rod and we just drill a hole all the way through, tap both sides, cut it to length in our lathe probably. You could even probably cut this on a saw. If this was a nice fractional length, you could buy a standoff like this from McMaster Carr, but it's not a fractional length. It's something weird because of our the tube is 1 inch, which is nice, but this not being a fractional width here because of the material thickness kind of makes that annoying. But all of that is buying us our nice spacing here, so I'm totally okay with it. All right, so then let's set some appearances here. These should all be this light gray for aluminum, I think, because I think we'd all make these out of aluminum. Don't need to model anything over here. We will come back and add some fillets and everything to make this look nice later. But we have 2 other brackets to make. So let's make this bracket here. I'm not going to explain too much about what the 2 pivots are going to look like. I think we're going to just use some bolts as pivots just to kind of make things easy. But we're going to just add some kind of holes in place, and then we might decide what we're going to do later. So I have a rough idea, and I think I know what we're going to do, but we're just going to add some screw holes where these pivots are, and then the pivots will be done in the next video. So I'm going to create a sketch on this surface here, and then what we want to do is just decide like which holes we want to mount with. I think we want to mount with these holes and maybe this one. I want this part to not be, so I could mount with these 4 holes here, but then the part is going to be kind of this like T shape. And when you assemble it, it's going to be difficult to tell which direction it goes because the part does matter which direction it would go, but it's going to be a little bit difficult to tell which way you're supposed to assemble it. So I'm actually going to make the part kind of more of an L shape down here to pick up this pivot point and these 4 mounting holes, and then it'll be obvious which direction it goes. So I'm going to project those 4, and then I'm going to create just some lines, just kind of similar to what we did before. Actually, I'm going to back up. I'm going to do a center point arc. It's not letting me attach to that sketch geometry for some reason, so I have to create it out in space and then constrain it. And then we're going to go from here to there. These will not be quite straight, which is why I created 2 lines. Line tool. There to there, to there to there. This one needs to be horizontal, up to there. And I guess I could actually, yeah, okay. It's, I probably should be a little careful about, it's doing perpendicular constraints. I don't want like horizontal constraints on this stuff because, if I were to change the angle of this tube in my layout sketch, it could break this sketch. All right, so what I'm gonna do is I'm gonna select both of these parts and do tangent, select both of these parts and do tangent. And then I'm going to dimension the radius of this. Doesn't really matter. I think I'm just going to do 1/2 inch. That's probably overkill, but it's fine. From here to there, that'll be 0.24. It allows me to use this hole for something if I want to later on, because like I don't know what this mechanism is. It could be, I don't want to cover up this hole by making this like, if I did that, I made it 1/2 inch, I'd cover up this hole, which is annoying. And that material, that extra material when I do that, it's not adding any strength. This part being kind of kicked over to the side like this is not optimal from a strength perspective, but it's all right for this. If I were doing something, if I were doing this on a real mechanism, I might take into consideration, how much load is on this and whether I want this to be a different shape to be a little stronger, but honestly, it doesn't matter that much. I'm actually going to make this 0.375 because it's just giant. Actually, I think this ends up being pretty close to horizontal. What's the actual angle between these? It's like a quarter of a degree. Okay. That at least makes the part look nice. Okay, and then once again, because this is a really important hole here, um, I'm going to just sketch it in, and then just a simple extrude, new 0.08. I think we use the 80 thou here, plenty strong enough for the vast majority of applications. Okay, so that bracket's done. Once again, we'll add some fillets. Technically, this is a corner, so we'll fillet this too, although it's going to be completely invisible. Okay, so let's come down here. Now, this one we got to be a little more careful about. So, actually, I think we're probably okay now that I think about it. Let's pull up McMaster car here and air cylinders. I shouldn't have closed this tab earlier. Double acting, stroke length, 4 inches. Really, the bore size is all that matters. This universal mount one. Let's go to the drawing. Okay. So the outside diameter is this 0.86 number. So the whole cylinder is narrower than the tube. Now the thing to keep in mind here is we've got this fitting hole right here, and it's right beside the pivot. I'm kind of just, there's this like little expand thing. I'm just using the corner to point. We've got this pivot right here, and then we've got this fitting right here. And so because the fitting is going to stick out way past our tube, so like we're going to have the air cylinder on here, and the fittings are going to stick out to the sides just because of the orientation of the holes here. So we need to make sure that this fitting doesn't hit our bracket. That's really the only thing that we have to worry about. The cylinder body itself is narrower than the tube, so we're gonna have a bracket that looks very similar to this, except down here. And so the whole cylinder will just fit between those two brackets, no problem. We just got to worry about the fitting. And so this is 0.62 from the fitting to the pivot, looks like. So we just got to take into consideration that 0.62 minus some distance for the actual fitting itself. Probably minus at least a quarter of an inch, probably more like 0.3 or something, just to make sure. So that gives us, 0.32 to work with around this like distance that we can protrude out from the center of this, which is not much, but that's enough. So I'll show you what that looks like here. So what we're going to do is we're going to just kind of do what we did before, create a sketch here. I'm going to use probably these 3 holes. Actually, let me back up. I want more length here, actually. I want to use 4 holes, but I don't want to stick past the front of the cylinder. Yeah, you'll see why. The geometry here will make sense here in a second. So I'm going to go in here and edit the layout sketch, make this 2 inches because I want 1 more hole. And then the whole thing will update, and the tube feature will add another hole. Oh, it added it the wrong spacing. Okay, I need to edit this. Auto offset maybe. That's probably gonna break all my references. Yep. Okay, undo that. And offset from end. Oh, that's not gonna work. There we go. That's what I wanted. Does this break everything? It does. Okay. Well, I'm just gonna fix it. It's fine. This is the issue with with sketching in these holes like this, is that this will happen. So we need to edit this, and then what I'm just gonna do is just delete all of these, and then I wanted 5, so it's gonna be 5. That's just something to understand, is that when you base geometry off of these auto-generated holes like this, stuff's gonna break. It's just important to understand how to fix it. And this is gonna break sketch 5, and then I need to go in here because now I deleted those holes and recreated them, so their internal IDs are different. So they're all still there. It's just internally the ID number for that geometry changed, and so it doesn't know where to find it. So I have to just go and delete it and replace it. Okay, we should be fine now. Okay, so then if we go down to the end, edit the sketch that we created most recently, And then I'll just use these 4 holes, and that'll be fine. Basically do the same thing up here, create an arc, coincident to that, create a line from there to there, and then I'm gonna just project. Actually, no, I take it back. I'm gonna do this a little more cleanly, because if I were to change the length of this again, it would everything would break again if I just project the end of the tube. Although it's always gonna be the end of the tube, so I suppose it doesn't matter. So actually, I take it back. This is how you know I'm doing this live, as I'm just doing these videos live. It's like make mistakes and change things halfway through. So I'm gonna do that as a tangent there. And then I guess I'm going to do the same thing we did before, just straight up and then over and then tangent that. And then this dimension can be like we've been doing, 0.24 in case we want to use that hole. Okay, so then the question is this radius. Now we said, looking at the cylinder, we wanted to leave probably at least 0.3 radius around where the fitting goes, like a 0.3 radius around here, just to keep out of that kind of zone. But I guess we can be a little more precise with this. This is a 1/8 inch NPT. If we go to open McMaster car again and do push to connect fittings, we could actually look up like what the hex diameter of the fitting is. I think it's a 1/2 inch. I want 1/8 inch NPT. Oh, that's pipe size NPT. Yeah. So then I think I want elbow. Push to connect, universal thread. I don't want universal thread though. It's this one here, I believe. Okay, so it's tube OD would probably be quarter. It could be quarter, 5/30 seconds, and then it'd be an 1/8 inch NPT part that this part would screw into the air cylinder, and this part would be the tube. And then doesn't look like it actually says. Let's just go to the CAD. It probably shows on the drawing. Oh, it's 9/16 hex. Ooh, that's bigger than I thought it was. I don't think this is not the style that we actually use, so I don't know. I'm pretty sure the ones that we use are 1/2 inch. I don't know. Let's throw a 9/16 hex in the CAD and see what this looks like. And then I actually want to. Oh, I should have made this construction before I started. There might be a faster way to do that, but I don't know what it is. Let's put a construction circle around the tips. Let's dimension this as 0.5625. What is this diameter? Ooh, it's more than 0.3 radius. It's 0.325. So this, yeah, actually better representation here. Yeah, it's this one needs to go. Oh, gosh. That's fine. That can go. All right. Going to attach. This is a little overcomplicated the way that I'm doing this. I could try, I believe, I'm going to look up what this dimension is as well, because I think the automation direct fittings are the ones that we actually use on RoboChargers. Depending on what team you are, it might not be the case. Push to connect R thread, push to connect MPT. It's these. Hex body. I guess I can just look at the straight ones. That's fine too. It doesn't need to be the elbow. Should be the same. All right. 1/8 inch NPT push to connect. Push to connect tube. No, it's push to connect socket. And then 1/8 inch tube to 1032 threaded. 1/8 inch tube to 1/8 NPT. Oh, whoops. I did this wrong. I want I think I just do this actually. Yeah. Okay, 1/8 inch NPT, 5/30 seconds tube, 1/4 inch tube. I think they're all the same hex size, but I could be wrong. Now that I'm thinking about this, I kind of do want the elbow just to make sure it's not different. Let's do this. 1/8 inch NPT, 5/30 seconds tube, 1/4 inch tube. Yeah, this guy. All right, and then docs and drawings. I don't think we can actually, I don't want to download it. I'd have to open it. Let me just click this and see what this does. Oh, cancel. Let's look and see if it says in the data sheet. H, yes it does, sweet. Okay, hex diameter, what part number was this? ME1418N, 1418N right here. H is ½ inch. Okay, sweet. All right, that's what I thought. I thought it was ½ inch. So this should be 0.5. And then we know that I'm going to do a horizontal constraint between here and here. It doesn't actually matter because this could be anywhere on the arc and all the geometry is still valid. And so the reason that this outer circle is here is because this hexagon could be in any orientation. And so I just want to make sure wherever the corners are, no matter where they are in terms of rotation, when we screw the fitting in, we can clear the corners no matter what. Like I don't want to design this to only clear the flat and then the fitting have to be aligned perfectly to clear. All right, so then the distance from here to there is 0.62. So this is what we're working with. This here just needs to not be past that circle there. So we'll just pick some dimension. 0.3125 is fractional. Yeah, that's fine. Okay, that's what we'll do then. Okay, so then this once again will be 0.196, and then we will extrude this out. New 0.08. This should be material 5052 again. Actually, I didn't check. Did I set the material for this one as well? I think I forgot. Yeah, I meant to do that. Okay, 5052 for that, and then both of these need to be this light gray color. Okay. All right, and then basically that's the core parts modeled. We're basically done. The only thing we need to just do now is just go through and fillet stuff. So I think we'll just standardize on 1/8 inch fillets here, and pretty much we'll just do this all in one feature. Just go through. I think this is a good candidate for fillet all edges, actually, now that I think about it. We'll do this, and I think I can do multiple parts with this. Yeah, it looks like I can. Okay, now the only thing here is I need to select this face. So we need to actually hide this part. Select that face there, and then I can show this part again. These fillets are a little weird. They don't line up, but that's okay. There's things we could do to make that work if we cared about it visually, but not worth the time. I think actually a bigger fillet would look better. No, I take it back. Kind of doesn't matter. We just don't want sharp edges. That's all that matters. Okay. All right. So then basically that's it. We're done. I think that's as far as we're going to go this week. We will handle creating assemblies, bringing in all the imported components. We'll bring in the air cylinder CAD model, bring in all that stuff, do fasteners, all that next week. So thank you guys for watching. I will see you guys next time.